You know, I was thinking about glitches in video games.
Oh, yeah.
You're playing along, and suddenly your character just, I don't know, walks into a wall and shoots up into the sky.
Yeah.
Or you see a car and its wheels look like they're spinning backwards.
Right. The physics engine just breaks. It totally pulls you out of the experience.
It does. We call it broken because it doesn't match our reality.
Yeah.
But today's deep dive, it puts this really wild spin on that. What if the glitches we see in the real world, specifically, how things behave at super high speeds, aren't actually glitches in reality at all?
Okay.
What if they're just optical illusions that we've mistaken for, like fundamental laws of physics?
That is a bold premise. We're basically looking at research that says we might have rewritten the laws of the universe just to account for what is, at the end of the day, a camera angle problem.
The camera angle problem.
Yeah.
That feels like a massive understatement. We're talking about special relativity here.
We are?
This is Einstein equals MC squared, the whole deal. It's the secret cow of physics.
It is. But the source material we're looking at today, it challenges the very foundation of that idea.
Yeah.
It suggests that Lorentz contraction, the idea that objects physically shrink when they move really fast, might just be they call it a math trick.
A bookkeeping error that we just accepted as reality.
That's the claim.
So our mission today is to see if we can dismantle that idea of shrinking space and replace it with something the sources call tilted simultaneity. And to do it, we're reviving some old ghosts.
Descartes, Newton, and a very specific astronomer named James Bradley.
And to get our heads around this, we have to look at the universe not as some, bendy, warping rubber sheet, but as a grid, a rigid, absolute grid.
Exactly.
Okay, so let's set the scene. The sources ask us to imagine a Descartes coordinate space. For anyone who hasn't touched geometry in a while, what does that look like?
Just imagine a giant, infinite 3D scaffolding, like a perfect, rigid jungle gym that fills all of space. It's the absolute stage for the universe.
This is what Isaac Newton believed in.
It is. And it's the world Maxwell imagined for his electromagnetic fields. It doesn't curve, it doesn't bend, it doesn't care if you move through it. It's just there.
Okay, so we have this invisible, rigid grid. Now, we need to put something on it. The sources talk about an Earth train.
Right. So imagine this massive train platform moving along the x-axis of this grid. And it's moving fast. 10% the speed of light.
0.1 c.
Yep. And on this train, we've got the most famous failed experiment in history.
The Michelson-Morley experiment.
The one that was supposed to prove the ether existed. Just a quick refresher for everyone. It's a device, 2 arms at right angles. You split a beam of light. One beam goes forward and back, the other goes sideways and back.
And the logic was super simple, right? If the Earth is moving through this ether, like cosmic wind,
then that wind should blow the light around. The beam going forward into the wind should take longer than the one going sideways.
But it didn't.
No. When they ran it, both beams arrived at the exact same time. 0 difference.
Which back then was a full-blown crisis. It broke physics.
So Einstein and Lorentz came along and said, okay, wait. The only way this makes sense mathematically is if the metal arm of the machine physically shrank in the direction it was moving.
That's Lorentz contraction. The train gets shorter, so the light has less distance to go, and it arrives on time.
It's a very neat mathematical fix. It balances the equation perfectly.
But our source material today just yells, objection.
It does.
They say this whole explanation enslaves light, which is pretty dramatic language.
It is, but it gets the critique across. Einstein's theory basically assumes that light is enslaved to the reference frame of whoever's watching.
So, like the classic textbook example. I'm on a train, I shine a flashlight from the floor to the ceiling.
To you, on the train, that beam goes straight up and straight down. It's vertical.
Right. And if I toss a coin, it does the same thing. It lands back in my hand because it shares my momentum.
But here's the crucial question the source asks. Why should light care about the momentum of your flashlight?
Light doesn't have mass. It shouldn't get carried along like a coin does.
Exactly. The source says we should think about it like rain hitting the side window of a moving car.
Okay.
If you're driving fast, does the rain fall vertically down the window?
No, of course not. It streaks backward. It hits the glass at a slant.
That's what the source calls the drift reality. It argues light moves through the grid, totally independent of the train. So as the light moves up toward the ceiling, the train itself is moving forward underneath it.
So relative to the train, the light should look like it's drifting backward.
It should. So Einstein says the light is glued to the train. This new theory says, No, the light and the train are two separate things moving through the same grid.
They don't hold hands.
Correct. And to prove that light actually behaves this way independently, the source brings in the hero of our story.
James Bradley.
James Bradley. The author calls him Bradley Senpai, which...
Yeah, that tells you how much they respect this guy.
It certainly does. So Bradley was an astronomer royal in the 1700s, and he discovered something called stellar aberration. And honestly, this concept is the main weapon the source uses to attack relativity.
Okay, so let's unpack stellar aberration. There's a telescope anatomy.
Yeah, it's basically the umbrella problem. Imagine you're standing in a rainstorm, and the rain is falling perfectly straight down.
Right. If I stand still, I hold my umbrella straight up.
Simple enough. Now, start running. If you keep that umbrella pointed straight up, what happens?
My legs get soaked.
Why?
Because I'm running into the rain. I have to tilt the umbrella forward to block the drops.
You have to tilt it to catch the rain. Bradley realized the exact same thing happens with starlight and telescopes. If you want to see a star and the Earth is moving sideways through space...
You can't just point the telescope straight at it.
You can't, because in the tiny amount of time it takes the starlight to travel down the tube from the lens to the eyepiece, the Earth is moved.
So the light would just hit the side of the tube, you'd see nothing.
Precisely. You have to physically tilt the telescope forward to match the Earth's speed.
And this isn't just a theory, right? We actually do this.
We have to. Bradley measured this tilt in 1725. It's a physical fact. An observer's motion changes the angle the light seems to come from.
So what the source is saying is, we know Bradley is right. We know we have to tilt the telescope. So why do we forget to tilt the idea of the light clock on the train?
That is the core of the argument. The source claims that standard relativity just ignores this Bradley tilt in its thought experiments. It treats the window of the train like a static 2D plane.
But if we respect Bradley, we have to admit that while the light is crossing the train car, the car itself has moved.
Which means the light travels a longer diagonal path through the grid.
And if it travels a longer path, it must take longer to get there.
It has to.
Which puts us right back in the crisis of the Michelson-Morley experiment. If the light physically takes longer to go forward and catch that mirror, why didn't the experiment show any delay?
Well, Einstein said the arm shrank.
But what our source says.
No! You don't need the arm to shrink. You need to look at your clocks.
Okay, this is where we get into the tilted simultaneity plane. And I'll be honest, my eyes glazed over a bit when I first read that phrase, but the visual is actually pretty helpful.
It is. So we usually think of now, the present moment, as a flat floor. Everyone on that floor is at the same time, say, T0.
My now is your now.
Exactly. But the source suggests that for a moving object, like our Earth train, now isn't a flat floor, it's a ramp.
A time ramp.
A time ramp. Think of the train moving along that x-axis. The source says that because of this motion, the synchronization of the clocks on the train actually tilts the front of the train. It's in what the source calls the shallow past.
Shallow past. Okay, what does that mean in plain English?
It means the clock at the very front of the train is effectively offset into the future compared to a clock at the very back.
So the clocks on the train aren't all reading the same time?
Not from the grid's perspective, no. And here is where the magic happens. Let's look at that forward beam of light again. It leaves the center and starts chasing the mirror at the front.
Right, and the mirror is running away, so light has to travel farther. There's a real physical delay.
A huge delay. In a purely Newtonian world, that delay would show up in the experiment, no question.
Input.
But because of this time slope, the clock at that front mirror is physically located higher up the time ramp. It's set to a time that is ahead of the clock in the center.
So, wait, the light arrives physically late.
But the clock it hits is set early.
They cancel out.
They cancel out, exactly. The source calls it a magic cancellation. The physical delay from the light chasing the mirror is mathematically erased by the time offset of the clock it's heading towards.
That is actually kind of brilliant. It's like if I'm running 10 minutes late for a meeting, but I secretly set the clock in the conference room back by 10 minutes.
Perfect analogy.
So I arrive on time.
You didn't run faster. The hallway didn't shrink, you just messed with the clocks.
So the Michelson-Morley null result isn't because space warped. It's because the time slope was hiding the delay all along. A cosmic bookkeeping trick.
Or just a geometric consequence of how we synchronize things. It implies we've spent 100 years chasing a warping universe when maybe we were just looking at a tilted graph.
Right, okay, but I have to play devil's advocate. If this is just geometry, if this time slope just happens when you move, why doesn't it happen to everything? What about sound?
The source anticipated that, and they have the lake analogy for it.
Right, the donut boat.
Donut boat. Imagine the Descartes grid is now a perfectly still lake. And on that lake, we have a boat hull shaped like a perfect circle, a rigid ring.
And we're moving this donut boat across the lake at half the speed of sound.
Very fast boat, yes. Now, we send a sound ping from the center to the edge. The simulation in the source shows a massive time difference.
Oh, big.
The sound takes 2.66 seconds to go forward and back, but it only takes 2.3 seconds to go sideways and back.
So the forward trip takes longer, the gap is real, and it's measurable.
It is. And crucially, the boat doesn't hide it, because the boat is rigid. It's a dumb object. The atoms in the boat hull don't care about the speed of sound. They don't magically offset their own internal timing.
So a Michelson-Morley experiment with sound would detect the motion.
Absolutely. Sound fails the test.
So why is light special? Why does light get the time slope and sound doesn't?
Because we define our time using light. That's the key. The synchronization of all our clocks depends on sending electromagnetic signals back and forth. When you sync clocks with light, you bake that slope right into your measurement system. You create the offset that hides the delay.
It's a self-fulfilling prophecy. We're using the ruler to measure the ruler.
You got it. And this leads to a really cool visual about the shape of things. The source talks about radar distance.
The part about the ellipse.
Right. So if you're standing on the shore watching that donut boat move, and you try to measure its shape using sonar pings.
The echoes from the front would take longer to get back to me than the echoes from the sides because the boat's moving away.
Correct. So if you then map out the shape based on those return times, the circle looks squashed. It looks like an ellipse.
It looks like it shrank. It looks like Lorentz contraction.
But did the boat physically get crushed? Did its atoms squeeze together?
No. It's just an illusion created by the signal delay.
Bingo. The source argues that special relativity is, in effect, confusing the radar image for the physical object. We see a squashed ship because our measurement tool light is slow. But physically, the ship is fine.
That's a huge shift in perspective. You're saying the math of relativity isn't wrong. It's just...
It's describing a measurement artifact.
It's describing the photograph, not the thing itself.
It's describing what we see, not what is. And that brings us to the Blender analogy, which I think is the strongest tool in this whole deep dive.
The 3D rendering software.
Right. Let's go back to our camera eye floating high above the grid at z equals 100. The source asks, when you render a scene in a video game, are you seeing a snapshot of the world at one single instant in time?
I mean, I would assume so. It's one frame.
You're not. You're seeing what physicists call retarded potentials.
Delayed signals.
Delayed signals. Think about it. If you're looking at a huge floor, the light from the far corner might take, say, 10 nanoseconds to reach the camera, but the light from the center only takes 5.
So the image I see is a stitch-up. It's a patchwork of the past.
It's a composite of different pasts you are never seeing now. You are seeing the center from 5 nanoseconds ago and the corner from 10 nanoseconds ago, all in the same image.
The render versus the mesh.
Yes. The mesh is the grid, the absolute reality at t00. But the render, the image you see on the screen, is warped by the travel time of light. The source argues relativity's mistake was assuming the simultaneity plane was the render.
We mistook the delayed photograph for the territory itself.
And because that photograph is distorted by delay, we invented curved space-time to explain the distortion instead of just saying, oh, that's just signal lag.
This feels, it's a really cool theory, but is there anyone who actually applies this absolute grid logic in the real world? Or is this just philosophy for people who don't like Einstein?
This is where the source plays its ace. The engineers.
The Zion-Chat School of Engineering Realism.
Exactly. The source points to GPS. We all use it. It's based on satellites moving at high speed with incredibly precise atomic clocks.
And we're always told that GPS proves Einstein right because the clocks drift. Time dilation.
They absolutely do drift. But the question is, how do the engineers fix it? Do they use general relativity's curved space-time math in the navigation software?
I mean, that's the story we're told.
Well, according to this deep dive, not really. The argument is that engineers use Newton's absolute time and Descartes' absolute grid. They use a system called the ECI frame Earth-centered inertial.
Which is, it's a fixed grid.
It's a Newtonian grid. When a satellite clock drifts, they treat it as a clock error. They don't say time itself has warped here. They say this ticker is off by 38 microseconds. Let's add a correction.
They force the world to fit Descartes' map.
They force it to fit the absolute grid. They validate the Earth train logic. They acknowledge the signal delay, they acknowledge the motion, and they correct for it to match the one public standard of time.
So the engineers are the secret keepers of the old physics. They nod to Einstein in public, but in the server room, they're using Newton.
They're pragmatists. They just care if the package gets to the right house. And the source lists the heroes of this way of thinking. Galvani, Romer.
And Descartes and Newton.
The ones who provided the public standard, the grid that just works. The argument is that theoretical physics became math drunk, claiming the grid doesn't exist, while engineers were quietly using it to guide our world.
That's a fascinating disconnect. Theory says everything is relative, but engineering says I need a fixed grid or the drone crashes.
Precisely. The engineer needs the clocks to agree, period.
So let's zoom out. What does this mean for you listening to this? We've gone from shrinking trains to time slopes to GPS. If this is true, how should we look at the world?
I think it changes how you see reality. We're so used to thinking that our observation creates reality, that the observer is king.
But this view says the observer is just a camera with lag.
A camera with lag. The universe is out there, rigid, real, existing in this massive now that we can never actually see. We're trapped in the render.
The retarded potential movie.
It's a humbling thought, isn't it? The source asks. If what we call reality is just a slice of a light cone, a collection of signals all arriving late, are we ever actually seeing the world as it is?
Or are we just watching a post-processed movie where the editors, our brains, our physics, has synced everything up to look simultaneous, even when it isn't?
It forces you to distinguish between the map and the territory. The map, what we see and measure, is tilted, it's distorted. But the territory might just be that boring, rigid scaffolding Newton dreamed of.
And it makes you look at the night sky differently.
It really does. Next time you look at the stars, think of James Bradley. Think about the tilt. You aren't pointing your eyes at where that star is right now.
You're tilting your head to catch the rain of light from where it was.
And somewhere, underneath all those tilted angles and delayed signals, the grid is just there, holding it all together.
Unseen, but essential. This has been a mind-bending one. Keep questioning the grid, everyone. Thanks for diving deep with us.
See you next time.